Welcome to a brand new MR Math Explainer. Today, we're going to master the fundamental laws of calculus and actually engineer solutions to broken equations. Honestly, if you've ever wondered how math can perfectly describe the seamless flow of our physical reality, well, you are in the exact right place. Let's get into it. So let's start by thinking about physical phenomena for a second. When you consider things like, time passing, or a car cruising down the highway, or even just a person growing taller, all of these processes are inherently continuous, right? They happen gradually. You don't just instantly teleport from point A to point B, and time definitely doesn't skip from noon directly to 1 p.m. without hitting literally every fraction of a second in between. In this explainer, we're going to look at exactly how calculus manages to capture this beautiful, unbroken reality. Here's our quick mission briefing for today. First, the rules of continuity. Second, 3 types of discontinuities. Third, the Intermediate Value Theorem. And finally, solving piecewise puzzles. All right, part 1, the rules of continuity. We've got to start with the absolute mathematical law of continuity. This really translates our physical reality into a strict standard. Visually speaking, continuity means a graph has absolutely no holes, no breaks, and 0 sudden jumps. Basically, you can draw the whole thing without ever lifting your pen. And mathematically, it just means a tiny shift in your x value produces only a proportionately tiny shift in your output, your f of x. But, to prove this rigorously, mathematicians aren't just going to rely on the whole drawing with a pen trick. Nope, they use a very specific test. Enter the 3-step test for continuity at a specific point, which we'll call A. Because, let's be real, mathematicians never trust what they can just eyeball. Every single continuous function has to pass this test flawlessly. Step 1. The function must actually exist at that point, like there has to be a set destination. Step 2. The limit as x approaches a has to exist. This means whether you're traveling from the left side of the graph or the right side, you are heading toward the exact same coordinate. And step 3. The limit must perfectly equal the actual function value, so the path you're traveling actually connects to the destination. Now, if a function passes this test at literally every single point across an interval, we say it's continuous on that interval. But if even one of these steps fails, the whole system breaks. Which brings us to part 2, 3 types of discontinuities. So, what actually happens when the system fails? Well, not all breaks are created equal. First up, we've got the removable discontinuity. Imagine you're driving on a perfectly smooth road, but there's a single, tiny pothole. The limit totally exists. Both sides of the road are leading to the exact same spot, but the actual point itself is missing, or maybe defined somewhere else entirely. It fails step 3 of our test. Now, we call it removable because it's super easy to fix. You just redefine that one single point. Easy. But then, look at the jump discontinuity. This one is way more severe. The limit from the left and the limit from the right are completely different numbers. It is literally like a collapsed bridge, where the two ends just don't align at all. The overall limit doesn't exist, which means it completely outright fails step 2 of our test. And then we have our third anomaly, the infinite discontinuity. Here, as you approach a specific x value, the system basically just overloads. The function's values aren't settling on a solid number. Instead, they become arbitrarily large, just exploding upward to positive infinity or completely plunging to negative infinity. Think of a vertical asymptote, kind of like what happens with a function 1 divided by x as x gets super close to 0. The limit fails to exist here simply because infinity isn't a coordinate you can actually reach. All right, part 3, the Intermediate Value Theorem. Let's see how these rules build into one of the absolutely most powerful tools in our calculus arsenal. Now, while this formal definition might look a bit dense on the surface, it's actually making a really profound and super intuitive claim about the physical world. It basically requires a function to be strictly continuous on a closed interval. And if it is, the theorem guarantees that the function will hit absolutely every single value, which we'll call n, between its starting height and its ending height. Let's use a real-world scenario to make sense of this. Imagine you're out mountain climbing. Altitude is a continuous function of time, right? You don't just glitch and skip through space. So if you start your hike at 1,000 meters and you finish up at 2,000 meters, the Intermediate Value Theorem states that you absolutely must have crossed the 1,500-meter mark at some exact moment during your trip. Because your path doesn't have holes, it doesn't have jumps, and you definitely didn't hit an infinite asymptote, you are physically forced to cross every intermediate altitude. To get from point A to point B on a continuous path, you just have to trace every single value in between. It is a mathematically guaranteed reality check. Moving on to part 4, solving piecewise puzzles. Okay, it's time for the boss fight. In calculus, we're pretty often handed a broken piecewise function. For instance, imagine a scenario where x squared meets c times x exactly at the coordinate x equals 2. Our mission is to find that unknown constant c to engineer a perfectly seamless bridge between them. So how on earth do we force this broken system to actually become continuous everywhere? We fix it by basically weaponizing step 2 of our continuity test. We just demand that the left and right sides meet. So in our example, we spot the handoff point at x equals 2. We calculate the limit from the left. Well, 2 squared gives us a height of 4. Then we calculate the right limit, which is c times 2, or just 2c. And here is where the magic happens. We deliberately set them equal to each other. 4 equals 2c. We are literally telling the equation I demand that the left side and the right side meet at the exact same coordinate. And from there, we just solve the resulting algebra. Once the algebraic smoke clears, we find our exact missing value, c equals 2. And by plugging that 2 right back into our original piecewise function, we completely heal that jump discontinuity. The x squared bridge and the 2x bridge now lock together perfectly at the coordinate 2, 4. It passes the 3-step test with flying colors and makes the entire function beautifully continuous everywhere. You have just mathematically engineered a fix. How cool is that? Well, consider this mission complete. You've successfully mastered continuity at a specific point, you've learned how to identify system glitches, and you even wielded the Intermediate Value Theorem. But hey, definitely stay curious. We've tamed what happens locally, sure. But what happens when our inputs just never stop growing? When our mathematical limits stretch infinitely far out along the x-axis, the rules of reality kind of warp entirely. So what does infinity really look like? Keep asking questions, and I'll see you in the next explainer.